Good morning, class. We are looking at section 4.6, the last section in this chapter, antiderivatives, also known as differentiation, and the session is being recorded. Many differentiation formulas, you got to be absolutely comfortable with it to move on. It is vital that you be very comfortable. So remember, in order to do division, you have to know multiplication. To do subtraction, you got to be comfortable with addition, the reverse process. I can't emphasize this enough. Integral calculus has two parts. The differential calculus that deals with the instantaneous rate of change and slope of a tangent line. Integral calculus that deals with accumulated change and area under a curve. Both refer to what's called a limit, and they are related as a result. Integral is the opposite of a derivative, also called antiderivative. So what is the question? The question is, given the derivative of a function, what is the original function? That's the process. The antiderivative of f of x is the set of functions. It's a family of functions class. Capital F of x plus c, such that the derivative of capital F of x plus c is lowercase f of x. C is the constant of integration. Understand, the derivative of any constant is zero class, right? So if I have 5 or 2 or 1 or 0.1 makes no difference. Its derivative is zero. Because of that, when you differentiate, it gives you a unique answer. But when you go back and you do antiderivative, anti-differentiation or integration, it gives you a family of functions, okay? It gives you a set of functions. Anti-differentiation is often called integration. To indicate the anti-differentiation of x squared is 1/3 x cubed plus a constant, we use this notation. This is an elongated S. We'll discuss this further in the next section. It refers to summation, and it was used by Leibniz. So in general, the integration of f of x dx is capital F of x. Normally, the setup is such that capital F prime is lowercase f in the concept of integration. So the integral of lowercase f of x is capital F of x plus c, and this indicates the independent variable is x. So if we have two functions, capital F and capital G, and in both cases the derivative is lowercase f, so f and g are considered antiderivatives for lowercase f. Therefore, f and g must be the same with the exception of a constant. So g is capital F of x plus a constant. That is the case, everybody, okay? That is the case. Let me just quickly fix something here. All right, let's look at some warm-up examples before we discuss the formulas in general. When we look at this example class, it's important to see what the question is. The question is, think of a function, you differentiate, it gives you 8. And remember, your independent variable is x. Can anybody think of a function whose derivative is 8, class? Think of a function, the derivative is 8. What would that be?
8x.
8x, and then we add a constant. To prove that, we differentiate the right side, and we get 8. The next part, 3x squared dx. Remember, this is in general tells you what is the independent variable. So what is it that you differentiate and it gives you 3x squared? Can you think of a function that you differentiate and it gives you 3x squared? That would be x cubed and a constant. To prove differentiate this right side, it must give you 3x squared, and it does. E to the power of x dx. What do you differentiate to get to e to the power of x? That's what we are looking for, class. What do we differentiate to get to e to the power of x? Anyone? What function we differentiate, we get e to the power of x?
E to the x.
That's it, itself, e to the power of x. And we add a constant. To prove this, all you have to do, differentiate the right side. And that must give you e to the power of x. It does. Now think about this last one, 1 over x dx. What do you differentiate that results in 1 over x? Do you remember that, class? What do we differentiate to get 1 over x?
Natural log.
Natural log, perfect. So natural log, and we put a constant. The reason we put it in an absolute value because of the domain of natural log, which is 0 to infinity. To check, differentiate the right side, you must get 1 over x without the dx. Let's discuss basic integration formulas. Here's the basic integration formulas. If you have a constant, any number times dx, first of all, this tells you the independent variable is x. Therefore, the answer is k times x, the same k times x, and a constant. Here's the power rule. I'm going to quickly go over the power rule and discuss the rest of this for you. Recall when we want to differentiate this, what did we do? We multiply by n, and the exponent goes down by 1. Now, if we are integrating, what would be the reverse process? We multiplied by n and we took down the exponent by 1. The reverse process, we have to take this up by 1, and instead of multiplication, it's division by n plus 1. And to check, let's differentiate the right side. If I differentiate the right side, what do I get? 1 over n plus 1 times the exponent, which is n plus 1. And I'm going to subtract 1 from the exponent. And I hope you realize we get x to the power of n back. So that works. This is, in fact, the justification as to why the reverse process is 1 divided by n plus 1, x to the power of n plus 1. All right, let's look at the rest of them. So this is the power rule. Very handy. K times f of x is k times the integral of f of x. If you look at numbers 3 and 4, we did this with the case of a differentiation also. If you have a constant, you can take it out or put it inside the integral sign. Differentiation works the same way. If you're adding, subtracting, just take the process step by step, term by term. All right. This thing works for every n except n equals -1, because n equals -1 is the same as x to the power -1 or 1 over x, which gives you natural log. In the case of an exponential, e to the power of x, the derivative and the integral are the same. However, if we have e to the power of kx, differentiation, we multiply by k, integration, we must do the reverse process, we divide by k. Now, as far as the sine and cosine and so forth, this you can look at them later on, we will discuss that again. But for now, just sine and cosine. The derivative of sine is cosine, okay? And the derivative of cosine is negative sine. Because of that, when you go with the reverse process, the integral of sine is negative cosine, and the integral of cosine is sine. Think about it this way. Start from the right side and go to the left. What is the derivative of sine? Cosine. So that works. What is the derivative of cosine? Negative sine. I know I have a negative, so I got to put a negative here. And of course, we need a constant. We discuss this further as we look at more examples. Let's start with power rule. So I go with the first one quickly. We want to integrate this. So this is the exponent. We take it up by one notch, becomes 8, and divide by it. So x to the power of 8, divide by 8, and a constant. Now, whether you write it this way or that way, it's your choice. But I hope you realize it is the power rule. You are adding 1 to the exponent, and then you divide by that. So if we have this one, what should be the answer? Anyone can give us the answer for this one?
1 over 100 x to the power of 100.
Beautiful. So 99, you add to it, becomes 100. So x to the power of 100 divided by 100. Now, again, you're writing it over 100 or 1 over 100 x to the power of 100. Doesn't matter. Don't forget the constant. Now, for a case like this, we did the same thing in the case of a differentiation. We changed square root of x to the power of 1/2. You remember that? So we have to do the same thing. Now, 1 over n plus 1, so 1 over 1/2 plus 1, x to the power of 1/2 plus 1. And I hope you realize that 1/2 plus 1 is 3/2. 1 divided by 3/2 makes it 2/3. So 2/3 x to the power of 3/2 and a constant. Same thing that we did in the case of a differentiation, we changed this so the power rule could be used. We changed it into x to the power of -3. So that's your algebraic technique. Now we use the rule. 1 over -3 plus 1, x to the power of -3 plus 1. Don't forget the constant. Now this one obviously is what? -2. So 1 over -2, x to the power of -2. You can also say -1/2. Now this x to the power of -2 goes down, becomes -1 over 2x squared. Don't forget we have a constant. So as you can see, the whole page is about the power rule. All right, exponential. Remember, when we are differentiating, we multiply by k. Since we are integrating, we're going to divide by k. Therefore, the answer here would be division by 4. So 1 over 4 e to the power of 4x plus a constant. Also, you can differentiate the result if you get e to the power of 4x. That proves you haven't made a mistake. And the key is in the beginning. If you have any doubts, we can check it. One over k, that means 1 over -3. And then you write the rest, e to the power of -3x and a constant. Needless to say, 1 over -3 or -1/3 means the same thing. If you recognize what this is, you don't have to rewrite it. Otherwise, you want to write it as e to the power of 1/2 x. Okay, so you're dividing 1 by 1/2, which makes it 2, and then you write the same thing, e to the power of x to the power over 2 plus a constant. Okay, so this 1 over 1/2 becomes 2. Now, if you recognize what you have here, it's fine. If not, you want to change this to 2 times 1 over x. So you recognize 2 times, now you have a natural log and a constant. Okay. We write this to make sure we understand we are dealing with a natural log. Same thing here, recognize it. So if not, rewrite 1 over 2x as 1/2 times 1 over x. Therefore, 1/2 the natural log x plus a constant. So this 1/2 really, if it helps, write it in the beginning until you get comfortable with that. Okay, class? All right, what I want to do, I want to give everybody a minute. Now that we've been through this, see if you can figure this out. It shouldn't take more than a minute. Okay. Let's see if we can figure this out, class. The integral of 2x to the power of 4 plus 3x cubed minus 7x squared plus x minus 5 dx. Term by term. Can anybody tell me the answer for the first piece? Two divided by 4 plus 1 or 5, x to the power of 5. Plus 3 divided by 4, x to the power of 4. Minus 7 divided by 3, x cubed. Plus 1 over, the exponent when it's missing is 1. So 1 over 2, x to the power of 2 minus 5x, and we have a constant. So I hope everybody recognizes that this one has exponent 1, and you add 1 to it. And you add 1 to it, becomes 2, and this is x squared. That's it. It's all using the power rule, step by step, term by term. When we dealt with differentiation, we did the same thing. We squared that. X minus 5 squared is x squared minus 10x plus 25. I hope everybody remembers this. A minus b squared is a squared minus 2ab plus b squared. So we are using this. So the first one squared is x squared minus 2 times the first times the last minus 2 times x times 5 is minus 10x plus, and then 5 squared is 25. This will give us 1/3 x cubed minus 10 divided by 2. That means minus 5x squared plus 25x, and of course a constant. We are using power rule term by term. Same thing here. When we did the differentiation, what did we do first? We cut this into 3 fractions. This is 1 fraction, x squared over x squared, which is 1. This is the second fraction. Let's actually do the drawing here. So this is 1 fraction, which is 1. minus 7x over x squared, which is minus 7 over x. Finally, 2 over x squared. So we make up 3 fractions. Now, one is very straightforward, minus 7 over x. If you have to, you can write minus 7 times 1 over x, so you see the natural log, plus 2 over x squared. We're going to change it to 2x to the power of negative 2. This way, we can use the power rule as follows. So 1 is very straightforward, gives you x, minus 7 times 1 over x minus 7 natural log. What about this part? Let's quickly show the work. This one, we get 2 over negative 2 plus 1, x to the power of negative 2 plus 1. And that is what? Negative 2 x to the power of negative 1. And we do the algebra. So we can see that 1 gives us x minus 7 over x minus 7 natural log of x. And this one we went through the process gives us this one, which we write it as negative 2 over x and a constant. Very straightforward class. I hope everybody is comfortable with that. And I hope you see a lot of algebraic techniques. Okay. Number 1, notice the independent variable is t, so be careful with that. Now, 1 by 1. 1, what gives you 1? T, because it's dt. If it was dx, we would say x. So because of dt, it's t. Cosine. What do you differentiate to get cosine? Sine, so plus sine. Remember, the integral of cosine is sine. Okay, so 1 gives you t, cosine gives you sine, and a constant. And you're done. All right, let's do this one. First, we're going to change this so that we can use the power rule. One over 1/3 plus 1, x to the power of 1/3 plus 1. And then this is algebra. 1/3 plus 1 is 4/3. 1 over 4/3 is 3/4. So 1/3 plus 1 is 4/3. The reciprocal of that is 3/4. Okay. And of course, we can keep it like that or change it. It's not a big deal. Minus sine x. The integral of sine is negative cosine. So this becomes a positive cosine and a constant. So this one, you keep it like that or you change it to this format. This is all basic algebra. Plus cosine and a constant. Solve the initial value problem. First, let's have a discussion as to what is the initial value problem. Any equation containing a derivative is called a differential equation. That's the definition. Remember the rational equation or a linear equation. Every equation has a definition. So any equation containing a derivative is called a differential equation. That's basically what we have been doing. A function which satisfies the equation is called a solution to the differential equation. An initial value problem is a differential equation along with a specified value of the unknown function called the initial condition. So first, to understand this, let's ignore that for now. I'm going to get to that and what it means and how it helps solving by just finishing the job as though we don't have this. Number 1, This means dp is this times dt. When you integrate, this is p is a function of t, so p of t, now we're going to integrate the right side. To integrate the right side, remember we divide by 3, right? So p of t is 2/3 e to the power of 3t plus c. There is absolutely nothing new yet, just as we have been working on this. Now, what is this initial value problem? There is a pair here, and I hope you realize the pair means 0, 1. So basically, you plug in the pair and it gives you the constant. What you have right now is called a general solution, which means it's a family of solution, which means there are infinitely many solutions because of the constant c. Now, replace the t with 0, replace the t with 0, replace the y, in this case, p of t with 1. Okay, so p of 0 is this, and it's equal to 1. As you know, e to the power of 0 is 1, so you're dealing with 2/3 times 1, which is 2/3, plus c equals 1, and c must be 1/3. Now we are going to replace the c with 1/3, and this is now a specific solution or particular solution. So what does it mean? Over here, we have infinitely many solutions because of the constant. Over here, the pair helps us get only one solution, a specific solution, a particular solution to this question. Let's look at another example. dy dx is 1 over x plus 1 over square root of x. Y is 5, x equals 1. And this is also an initial value problem because of this. The pair is 1, 5. This refers to the pair 1, 5. And we are going to ignore it for now, solve it as before, then we get to that. Meaning, let's deal with this. dy is the right side times dx. If we integrate, this becomes y or f of x, and the right side, we're going to work on it. So y is the integral of the right side. Okay. We change the x to the power of 1/2. We've done this many times by now. And we bring it up, becomes a negative 1/2. Why do we do that? So we can integrate using the power. So let's go term by term. 1 over x, that's a natural log, plus x to the power of negative 1/2. So 1 over negative 1/2 plus 1, x to the power of negative 1/2 plus 1, and a constant. So this gives you the natural log. This uses the power rule, gives you that. So let's simplify this. Negative 1/2 plus 1 is a positive 1/2. Therefore, this is 2 x to the power of positive 1/2. We rewrite this as 2 square root of x. So this is a general solution. So let's write this. General solution as before. Now we're going to add the pair, which will help us find the constant. And instead of a family of function, we will have a specific solution. Let us plug in 1 instead of x, 5 instead of y. ln1 is 0. This is 1. Therefore, 5 is 0 plus 2 plus a constant. Constant becomes 3. Now, this is a particular solution. I hope it's straightforward, class. Initial value problem basically gives us a pair which will help us find the constant. That's all there is to it, which is really an algebraic problem, if you will. Same thing here. We want to solve this, and this will give us the pair 2, 1. We're going to ignore it for now. So let's integrate capital F prime to get f of x without paying attention to the pair. 3x cubed, I hope you realize by now it's x cubed plus 3/2 x squared plus 7x and a constant. This is again a general solution, GS general solution, okay? Now we have the pair 2, 1. We are going to replace the x with 2 and f of x or y with 1. You're going to simplify. So 2 cubed, 8. This is 4 divided by 2, 2 and times 3 is 6. This is 14 and a constant, which means the right side is 28 plus a constant. The left side is 1. Therefore, the constant becomes negative 27, right? And we write capital F of x now as this function, which is a particular solution. PS, let's say for short, particular solution. So the moment we hear initial value problem, it simply means integrate or anti-differentiate and then use your algebraic techniques. This uses algebra class to finish the job and find the missing constant. Here's the last question. We are going to do this just as we did with the differentiation, meaning first we make it ready to be integrated by cutting it into 2 pieces, everybody. So x over square root of x plus 1 over square root of x. Square root of x is x to the power of 1/2. We use the quotient rule. The first one becomes x to the power of 1/2, the other one to the power of negative 1/2. So going from here to here is what matters. And whether you take 1 or 2 or 3 steps, it's up to you. The only thing I want to make a point of, everything we've done so far is algebraic steps. All algebra. Nothing is calculus yet. All algebra. Now you have only one step of calculus, which is add 1 to this, becomes 1/2 plus 1 or 3/2, divide by it. So 1 over 1/2 plus 1, x to the power of 1/2 plus 1. This one, the same thing, add 1. So 1 over negative 1/2 plus 1, x to the power of negative 1/2 plus 1. Needless to say, 1/2 plus 1 means 3/2. Negative 1/2 plus 1 means 1/2, right? So division by 3/2 is multiplication by 2/3. Division by 1/2 is multiplication by 2. all algebra, all algebra, and you're done.